Okay.
Hello, my name is Birring, and this video is a continuation of the remote field video which I actually recorded last week, and we will go more into detail now on the calibration and the setup to do the inspection. So just a review here, like I said, in the remote field region, the OD electromagnetic field is higher than the ID field, which is this region here. So the transmitter and receiver are separated from each other. There is a signal which goes from the transmitter, which is a continuous signal here, and it's about, let's say, 400 hertz when we are inspecting a tube which is 3/4 inch by 0.083 inch thickness. And so when there is wall loss here, or if there is wall loss here, this phase of this signal will shift, or it will actually, there will be a time change in this signal, and that's called the phase shift of the signal. And we actually plot that phase shift on the instrument using a polar plot, which I will show you on the other side. So here we have the calibration tube, which is right here, and it has a support plate. It has two grooves, which is a 360-degree groove here, support plate here, a ring, and this is another groove, but it's only 180-degree groove. A calibration tube, 40% 360 degrees, 60% 180-degree groove, and the support plate. So when we pull the probe here, it's going to see this small groove, which we call as the short, and which means that the groove length is smaller than the spacing between the transmitter and the receiver. So when you pull the probe, you will see this groove two times, which is here and here. So first the transmitter, and then it goes back to the balance position, then the receiver, which is the second signal, and then we are going to see the support plate, and then we will see the long groove, which is 60% and 180-degree groove. So initially, when you pull it the first time, what you will see is a signal like this, where the support plate is going at an angle, and then you see these two grooves here, 40% and 60%. So the first step is to rotate this polar plot. This is a polar plot here, and we rotate it to make the support plate horizontal. So this one is rotated, and we bring it down to here. So this is initially, and when we do the calibration, then we make it like this by rotating the support plate to make it horizontal. Once you have this support plate horizontal, then the next step is to make the depth curve. So the depth curve, we will make it on the short flaw, so which is like 40%, and then when you make the depth curve, it's a linear curve. Like I said, a remote field phase change is linear. So all you need is a single point to make the depth curve. You don't need, like in conventional eddy current, remember we made the depth curve on 5 different points, like 20%, 40, 60, like that. Here all you need is a single point, and then it makes a depth curve where 135 degrees is 0%, and all you do is pick up either the 40% or the 60%, and which is right here, and get the phase, and it will actually just put it here, and you pick one point, and it will make the linear depth curve. So this depth curve will be used to estimate the depth of the flaw. So now, just to give you some limitations and some highlights about the remote field. First of all, the remote field is linear. The phase delay is actually linear, and this is different than the conventional eddy current. So the depth curve and the phase delay for the remote field is a linear. And then also the pull speed for remote field is slow. As compared to conventional eddy current, we can pull conventional eddy current probes at 1.5 meters per second. Here we are just going to be pulling at about 300 millimeters per second, or 1 foot per second. So pull speed is slow as compared to conventional eddy current. and it's not a good technique for detection of small pits and small pinholes, so it will most likely miss them. It's basically a good technique for wall loss measurement, and that's what it should be used for. So now I will actually show you the next step when you do the inspection, how you reset the phase for the actual inspection in a heat exchanger tube. Pause it.
Okay.
So now we start the inspection in a heat exchanger tube, and this is what it's going to look like. This is a horizontal strip chart, vertical strip chart, and what you would see initially is you will see the support plate signals here. We have 4 support plates, and then you look at the polar plot and you get one of the support plates here. This is number 2, and then you look at the polar plot and you will see the support plate, let's say, going at this angle, and this is the wall loss signal, which is right here. So what you do is the support plate signal angle in the actual heat exchanger is not going to be the same as what you did on the calibration tube. So you have to reset the support plate back to 0 degrees. So once you go into the heat exchanger, you get the support plate here, and then you rotate it, get it back to 0. And then what you do is when you get the strip chart, it's going to look like this. You will see the support plate in the horizontal channel, and you will hardly see that in the vertical channel of the strip chart. So from here, it will actually go into here, and you will see support on the horizontal channel. And then what you do is, if there is wall loss, the signal is going to look like this, and then you go into the polar plot, the signal is like this, and from here you use the depth curve to estimate the depth of the flaw. But again, you have to make sure, are you using the long flaw or the short flaw, because the measurement will be different. So that's kind of you have to see the length of the flaw to apply the depth curve. So this has been kind of the whole description of the application of the remote field, and thank you very much.